Hi, my name is Matt Kuruc, and I'll be talking about Universal Scene Description and how you might use USD to build your asset pipeline. This talk's broken up into two sort of main parts. The first part we'll be talking about USD composition and sort of the underlying features of USD. Then we'll be reviewing sort of the roles of schemas in USD. Once we have that built up, we can start talking about the ModelAPI schema and how Kind and the ModelAPI work. And then finally, we'll talk about some example asset and shot structures. So at its core, USD was built as a language for collaboration. If you've ever opened up USD and USD stage before, you'll see that there's a bunch of prims, which are locations in scene graph arranged hierarchically. There's also each prim then has a set of properties, which are attributes and relationships. So if we had a sphere on a USD stage, the sphere would be a prim, and its radius would be a property of that prim. There's also various pieces of metadata which can be used to augment prims and properties and annotate them. These concepts hopefully map to various DCCs and file formats you've seen before. These are just sort of our names for those concepts. If you've opened up USD before, the tree view on the left represents the prims, the table below represents the properties for the selected prim, and then the metadata is in that corner there for the selected prim or property. That brings us to the composition operators, which are sort of the primary tools for expressing collaborative workflows in USD. Any USD stage can be composed of multiple layer files, allowing the users to override values. Inheritance can be used to have values on prims which can be shared and derived from other abstract prims. Prims may have multiple variants, which can provide various combinations of values, and the variant sets provide an interface to those various combinations of values. Lastly, we can reference external scene description into specific paths onto the stage. There's also sort of several advanced operators, which are more sort of specializations or variations of those sort of four concepts of layering, inheritance, variance, and referencing. We'll be talking a little bit about payloads later, and we'll be touching on instancing as well. To sort of provide a motivating example, I want to talk a little bit about a forest and what kind of work goes into just one tree in that forest. So our modeling department is going to model that tree. They're going to provide a mesh and some curves to represent the geometry of that tree. Our set dressing team is going to place that tree into a set along with a bunch of other trees. We might have in the shot context an automatic process like pruning, which goes in and deactivates trees that it deems to be unimportant. Our camera dressing artist may come along and say, actually, we want to reactivate that tree. That tree was important. And we're actually going to nudge it along. We're going to shift its translation value. And then lastly, our simulation department might come along and they might decide to add some wind, add some keep alive to that particular tree, and they might want to override the points on that tree. So the key takeaway is that there are many different providers of data for the final composed result. Not only that, no one department or workflow has complete ownership of any particular prim or value. It's for this reason that we like to call values in USD opinions. And so USD's kind of role in all this is to sort of mediate and assemble these sort of disparate values into a final composed result. So if you're working on a renderer that's consuming USD or any sort of import process that's consuming USD, you don't have to care about the pipeline that constructed the stage. You don't have to care about what file or what composition arc was used to sort of construct the composed result. You just worry about the composed result. That's a much simpler view of the world. Now, USD's core is sort of built around collaboration, and nothing is really built around computer graphics. So it's up to schemas to sort of bring things into the computer graphics space. Schemas don't really care how prims were composed. They don't change the results of composition. What they do is they answer questions like, where is the tree in space? What are the positions of the needles at frame 7? Do the trunk points vary over time? The sort of three primary types of schemas are, one is our concrete typed is a schema, and that's an interface specific to a particular prim type. So these are types that you can actually instantiate on a USD stage. You can create a cube, you can create a sphere, a mesh. There's also abstract typed schemas, and these are sort of shared interfaces across multiple concrete types. So a really common workflow might be wanting to traverse a stage and iterate over all the G-prims or all the boundables, and provide some sort of operation to anything that inherits from boundable. Abstract schemas sort of provide that sort of workflow. We also allow for a third type of schema, which we call API schemas. And these are sort of extension or non-hierarchical interfaces. They don't really fit into the standard USD type hierarchy, but they are a useful API to have. So for example, the collection API, we may want any prim type to be associated with a collection, so it sort of sits outside of the type hierarchy. If we're looking at some code here, we can access any prim on a stage. We can bind a schema to that particular primitive. We can retrieve an attribute from that particular schema, and then we can access the value at a particular frame. Now let's look at some other code here, and the key sort of takeaway from this slide is that both of these pieces of code are functionally equivalent. Whether I'm accessing the attribute via the schema or accessing the attribute via name, I should get the same attribute back. And similarly, the value that is provided should be the same as well. Schemas, again, sort of don't change the result of composition. They don't affect composition. Their primary role is to just provide a common meeting place so that sort of one team doesn't go off and say, hey, we want to have a sphere schema. Let's call our sphere schema, our sphere radius attribute radius. Another group says, actually, we're going to use diameter instead of radius. Another group decides to abbreviate it to just R. Schemas sort of provide that common meeting place to sort of help interchange and understanding and interpretation of what the USD data is. So those are kind of the two core underpinnings that kind of motivate the rest of the talk. Composition is sort of built around collaboration, and then schemas sort of bring the USD core into the computer graphics space. So now let's talk about model hierarchy, model structure, and how kind plays a role in all of this. So given the sort of features that we've talked about, we could actually kind of render this transform hierarchy. We can use the XForm schema to extract the transformation on all these different scopes. We can use the mesh schema to extract the points and extract the topology from all those prims as well. We're set to render this. We can do a lot of things with just the schemas. But there's kind of a question that their schemas by themselves aren't answering, and that's kind of what is important. And when we say sort of what's important, we're sort of saying what's a model, what's an asset, what were sort of the key components of this transform hierarchy. Well, so how could we figure this out? You might initially say, like, well, if something used references, maybe if something was referenced in, that's probably an asset, right? That's probably important. But, there's all sorts of different composition operators. Which ones do you key off of? And as your pipeline changes and evolves over time, we sort of kind of try to make sure that these kind of operators are invisible on the compose stage and that you're not really keying import or export behavior too much off of them. And additionally, scenes may get flattened, right? So you might have composition operators and they may get flattened out over at some point in the pipeline. You don't want to lose what was important because you froze something or locked something down. So that sort of brings us to the concept of kind and the ModelAPI. So USD sort of provides three core concepts of kind, and kind is just a piece of metadata that lives on a prim. So I could view this scene as an XForm called MU campus set, which contains an XForm called quad group, which contains an XForm called veg group, which contains an XForm called oaks group, which contains an XForm called tree oak 1. Or I could sort of view it from the much sort of simpler and much more useful for many operations concept of, well, we have an MU campus set, and one element of that MU campus set is tree oak 1, without sort of thinking about the sort of intermediate hierarchy. So if we were to sort of try a more complicated example, like let's say we wanted to model New York, we might divvy it up into its 5 boroughs. Then we might extract a Central Park set out as its own assembly as a part of Manhattan set. You may want to then bring in sort of some 2 elements like a terrain, which would be the Great Lawn. And we might want to put a picnic basket on that terrain. So we'll bring in those 2 guys as well. That picnic basket may come preloaded with a grape bunch. And that grape bunch may have 2 grapes, which were sort of deemed important. Model hierarchy lets us define what an asset is without caring about the file structure or the composition operators or how this thing was composed. We haven't talked about whether or not Manhattan set was done via references or via payloads or via sublayering in. We just know that it was important. If we want to talk a little bit more about the rules of what sort of constitutes something as an assembly versus a component versus a subcomponent, we like to think of components as kind of like atomic elements unto themselves. If you look, assemblies can sort of contain other assemblies or components, and subcomponents can be children of components or other subcomponents. But components themselves are a barrier of complexity. You can't have a component which is a child of another component. This kind of gives us a language for sort of talking about things at a higher level. We don't have to now think about things just as X-forms or meshes, but we can start to talk about, well, let's deactivate any component not in the frustum. Let's tag all of our components to be instanceable. Let's expose and track manipulator controls on all subcomponents in DCCs. To sort of further motivate this, let's talk a little bit about pruning and how pruning might leverage the concept of components. So if we have a forest here with a bunch of tree groups in it, we might want to say, let's get rid of everything that's outside of the frustum. Forests are expensive to render. Let's go ahead and try and make this cheaper. You might start by saying, like, well, just kill anything, any scope that's bound is outside of the frustum. And you'd start to do that, and you'd kill tree group 1. You'd kill tree group 5. And tree group 4, its bound intersects the frustum, but its individual subcomponent models don't. So we're just going to deactivate those at the component level, leaving the parent group active. Now, if someone makes an edit to the underlying set and they add a tree, because that tree's parent group has been deactivated, that tree will not show up in that particular shot context. This may cause all sorts of confusion. It might cause some scrambling. Wait, I added that tree. Why isn't it showing up? And, people have to go and start to debug this. So an alternative way we could have approached this is we could have said only deactivate things at the component level. Okay, so we get to tree group 1. We see all of its individual component models are out of the frustum. So we deactivate those guys. Same thing with tree group 5. And same thing with tree group 4. So now when the underlying set is edited and a new component is added, the parent group is active, and now this tree will show up. And so hopefully that makes the case for why having this sort of granularity is useful and why we don't want to necessarily apply operations at too high of a level. But what about too low? Is there a concept of potentially pruning too small of a granularity? So here's a tree. Its needles are intersecting the frustum, but the trunk isn't. So if we were pruning at just the individual G-prim level, at just the individual mesh level, we would lose the trunk and keep the needles. Now, if that tree was casting a shadow into the frustum, that might cast a weird shadow. That might cause confusion for lighting for why they're seeing the needle shadow, but not the trunk. If we had approached this at just the component model level, both would have been kept. And so that's kind of why we think component model is a useful concept. It just provides a single sort of atomic granularity where you can start to build workflows around what are the individual elements of your scene. Let's talk a little bit about Pixar component model design. It's important for us that we want to defer loading and traversal while still retaining boundability, asset-dependent analysis, as well as the access to the various variants and inherits that particular model may have. So if we had a tree pine asset, we would have a tree pine USD file, which has a root default prim of tree pine. That tree pine would have metadata called kind set to component, and it would also have a payload. And so that payload, if you're not familiar with it, is very similar to a reference. Payloads are special because they can be loaded and unloaded. And so you can open up a stage with all payloads unloaded and not pay for the composition cost until you need to load it later. That can help reduce the memory footprint as well as the time to sort of compose and load up a stage. So we have a payload USD file associated with this tree pine USD file. And that payload is going to bring in both the geometry and the shading. We're using references to bring in the geometry, and we're using sublayers to bring in the shading. Why are we using both? Our pipeline just kind of evolved this way. At some point, someone realized it was useful to be able to potentially mute shading layers, and so shading got moved to be a sublayer. You could achieve very similar pipelines using only references, using only sublayers, potentially using a chain of references where the payload references shading, which references geom. There's a lot of different ways you could express your pipeline. This is just how we've sort of evolved over time. So we talked about how important it was that we wanted to have the variants accessible above the payload. So what this basically means is that when the payload is unloaded, we still want to be able to change the variants. Why is this sort of important to us? Well, you could imagine if the variants weren't accessible above the payload, we might have to load the model and let it compose using its high level of detail variant just to change it to its low level of detail variant. If the variant is exposed above the payload, then we can switch from high to low before we load it. Similarly, we want the inherits above the payload. One common workflow we might have is we might want to say anything in class tree has its LOD variant set to low. And so we might have some opinions which are specifying that. It would be sort of awkward if we could only express that when the payload is loaded. We want to be able to see what the LOD variant would be set to with any opinions coming from inherits. Lastly, we said we care about the asset dependency analysis, and we also care about the bounding box. So the shading file may have lots of external dependencies. We might have like a global leaf shader or a global needle shader or global bark shader that we're referencing either in part or in whole. So there might be external dependencies that we want to know about beyond just the local shading file. And so we put that into the asset info's payload asset dependencies. Additionally, we may care about the boundability of that. And so we might want to compute the bounding box for the tree and bring that up into extent hint. Anytime we're diving into something below the payload and bringing it to the top of the asset, we call that process lofting. And so when the payload is unloaded, we still have access to lots of information about that particular tree. We have access to any assets it's dependent on. We have access to an approximation of its bound. We have access to any variant that we might want to change, as well as any inherits that we're sort of dependent on. So you can do a lot of things with just this bit of information when the payload is unloaded. Lofted variants, there's kind of an analogy here towards forward declaration. You don't have to bring all of the opinions of the variant above the payload. What you can just sort of say is, there's a variant set called LOD variant. One of those variants in that set is high. One of those variants is low. Don't specify any opinions in it. That'll get defined later once the payload gets loaded. And that's kind of how it's sort of like forward declaration. It's empty, it's going to be defined later. So we talked about component model structure at Pixar. Let's talk a little bit about some other constructs. So some other constructs you might have are assemblies, and in particular, you might have two types of assemblies, sets and character groups, as well as we'll talk about shot structure once we have assemblies down. So if we go back to our forest example, we're going to start with a forest USD file. We're going to start with a forest xform prim as the root prim with its kind set to assembly. We'll bring in a tree group 1 xform, and we'll plop a tree pine 1 into that tree group 1. And that's going to be a reference to the tree pine prim in the tree pine USD file. We'll also bring in another tree pine, and we'll bring in some aspen trees as well. And on those aspen trees, we're actually going to set the modeling variant on those guys. So we'll set one to full and one to bare. And we might know that one of those aspen trees is really important and it's going to have some hero work. So we might actually flag it as not being instanceable. So you can see that all of the trees in this particular set have been tagged as instanceable. Instanceable in USD, if you're not sort of familiar with that concept, really just makes primitives read only. So that way their composition can be shared across multiple prims. So this is how we might just go about constructing a set in USD. But there was one thing that we might want to add as well, not just the positions of the trees. We might want our forest to come pre-populated with a bunch of wind setups. So our simulation department may provide us with some default USD wind files, some overrides for the needles and the leaves on the particular trees. And so how would we want to go about applying these to the forest? Well, we can leverage the inherits composition arc that those trees have. So all of our pine trees are inheriting from a class called tree pine. All of our aspen trees are inheriting from a class called tree aspen. And so if we drop in a reference to wind caches, we can apply those to every particular tree in the forest. What's interesting about this is that these opinions will apply whether or not the tree is instanced. Because they're shared at the sort of class level, they affect everything. And so if you want to make edits to prims that are instanced, you can basically use classes as a mechanism for doing that. If we want to look at character groups as another potential example of an assembly, we can have a Sully group xform in a Sully group USD file, and that may contain Sully, which is a reference to the Sully body mesh. It may contain Sully hair, which is referencing his groom, and maybe a jacket, a piece of clothing that he's wearing. But in this case, we're actually going to set the kind equal to character group. And our Sully is going to be kind equals char, and our hair model is going to be kind equals hair, And our jacket model is going to be kind equals garment. And these aren't part of the 3 core kinds that we talked about. Kind is an extensible concept, and you can have different hierarchies of kinds. So at Pixar, we actually allow for 4 different subkinds of component: hair, char, garment, and kind of a catch-all called prop, as well as a couple of different assembly kinds, which include set and char group. And this lets us specialize beyond just assembly and component. Most of the stuff that we try to open source will be keying off of the concepts of assembly and component, but kind is just metadata and it's extensible. So there's a configuration file where you can set up your own kinds if you want more than just the defaults. So now if we want to look at a potential shot structure, then we might have a M050 100 USD file, which represents the shot. Effects may have their own USD file, animation may have their own USD file, and there might be a sequence USD file that every shot in that sequence inherits from. And the sets department might decide to put some opinions in that particular sequence layer. So they might decide to reference in the MU campus set for the entire sequence. Our animation pipeline may decide to reference in the Sully group, Xform, and then provide sparse overrides on top of that model. And our effects team may come in and they just might want to embed geometry directly in their layer. They might not need this referencing or this sort of logic. They just may want to add some geometry directly to the particular shot. And so what you can see here is in the same shot, 3 different departments all using different composition operators and different sort of techniques to sort of bring things together into the final shot. We have the sets department, which is just using straight up referencing, nothing super fancy. Our animation is using referencing plus sparse overrides to get the animation into the shot. And then our effects department's just blatantly dropping geometry in. So just to kind of bring this back to the idea of USD as a language for collaboration, it basically, at the end of the day, it's built around how we want to work together, and it provides a lot of different options for expressing how you can work together as a studio, as a pipeline. We've talked about the core of USD as composition and how schemas kind of bring things into the computer graphics space. And with that sort of foundation, we brought up the ideas of why ModelAPI and Kind are kind of important, and how you might structure your assets and shots using ModelAPI and Kind. This has been the talk on how you can use universal scene description to sort of build and approach asset pipelines. For any sort of more information, please go to the USD website at graphics.pixar.com/USD. In particular, you might want to check out the USD glossary, which has lots of detailed information on all the different terminology and composition operators we talked about during this presentation. Thank you.